Welcome back to Tracing the Sky. So today we're going to take another step along Aristarchus' journey. Last time we looked at how he was able to relate the diameter of the moon to the diameter of the Earth's shadow. And today we're going to see how he can figure out the relationship between the diameter of the Earth's shadow and the Earth itself. And that's going to give him one next big piece towards his ultimate goal. So let's hop in and take a look. Okay, so let's look at how he's able to do this. Now, we're not going to look at all of his exact methods. Some of what we'll cover is what Aristarchus thought or the Greeks knew in general. Some of it's going to be Archimedes. The general ideas are true. I'm trying to be a little selective based off of what I think is easiest to understand. They all arrive at the same answer though, so there are multiple ways to tackle this problem, and I might do videos in separate videos on Aristarchus's exact method. I just find the one I'm going to show you today to be the easiest to understand. So let's look at that particular method. Okay, so the first thing I want to look at is a solar eclipse. In the last video, we looked at a lunar eclipse, right? Lunar eclipse is when the Earth gets between the sun and the moon. Solar eclipse is when the moon, as you can see here, here's the moon, is between the sun and the Earth. You can even see here, the moon's shadow is being cast on the Earth. Now, if you remember, this goes back a few videos. Aristarchus noted that we know that the moon and the sun appear to be the same size in the sky because of a lunar or solar eclipse. That's one of the reasons, at least. When we have a solar eclipse, the moon just covers the sun. Now, I want to explain a little bit more about the geometry and how they understood this, how he was able to also prove geometrically that the sun was proportionally further away and larger than the moon, right? That because of how they appear to us here, because they appear to be the same size from our perspective at Earth, that the distance must be proportional to their sizes, that if the sun is 19 times further away, it must also mean that it's 19 times bigger. So I want to prove that geometrically because it will be really important for our next step. Okay, so the first thing I want to do is just understand how shadows work, and especially in the relationship of the sun, the moon, and the Earth. So here I've drawn those three. Here's the Earth, here's the moon, and here's the sun. And I've drawn the sun way smaller than it is and way too close. But I want to just illustrate a point. First of all, what's happening here? Well, the sun is the light source. And the way to think about light is that it's emanating in every direction. So if you're thinking about light at this particular point, the light's not just going out in this direction. It's also from this point going this way and this way and this way. Think of it like an arc that's radiating out from every point. So you can think of it like light coming from the sun in every single direction. Now, you can think about the moon as blocking some of the light. So there's still light all in this area hitting the moon, but this is kind of the boundary. There's still light all the way around here, but the light that is at the boundary of the moon is being blocked by the size of the moon, right? The edges of the moon are blocking some of the light. So we can represent the light that's reaching the Earth, or not reaching the Earth in this case, by looking at these boundaries here, right? These are the boundaries of the moon that's blocking light. Everything between here is illuminated, right? So you can draw, light between here, and you can draw light out here. So there's light out here and in here, but these are the boundaries that light is not able to escape or get past. So none of the light is reaching the Earth. Now, in our case, though, we know that during a solar eclipse, there is some light that's reaching the Earth, right? If you were to ask somebody that's living in a different place at the same time that you're experiencing a solar eclipse, they wouldn't be experiencing it. They might just say, no, it's just daytime, right? So let's explain that phenomenon. There are two things that control the size and nature of the shadow: how big the light source is and how much further away it is. What you can see here really quick is, let's say I just made the sun way, way bigger. So if I make the sun larger, so I make the sun larger, you can see it and leave it at the same distance. So I leave it at the same position. You can now see that there's light coming off of here that would be blocked by the moon. But if you look at the outer edges of the sun, right, remember from this point, light is going in every direction, including this direction, well, you can see that the light is able to reach the earth, that quite a bit of light is able to reach the earth. All of this light is able to reach the earth, right? So you can see that it's converging, and the moon isn't able to block much of the light. In fact, if we kind of make a tangential here, all of the light from this point outside, including some of the light that's coming off this part of the sun, is able to make it to the earth. So we still use the moon as kind of our boundaries, right, for the light. So it's still blocking some of this light. So this part's still illuminated, but there's a lot more of the light that's able to make it past. And depending on how much further away, it might not even cast any shadow, depending on how large and further away it is. So in order for there to be a shadow, it has to be further away enough and small enough in order for the moon to block some of that light. Eventually that light will converge if it's big enough, but the shadow size will be determined based off of how big the object is and how much further away it is. So let's see what that implies. Okay, here's where it gets really cool, and we can use some math that we learned to answer this pretty easily. So remember, what we see in the sky is that the sun and the moon appear to be the same size. We also know that if something is further away from us, it begins to appear smaller. So either the moon and the sun are the exact same size at the same distance away from us, or the sun is much further away. And remember, Aristarchus proved that the sun was 19 times further away based off of a half moon, right? In that angle. Now here's what's really interesting. If you represent the moon as a right angle triangle like this, right? So the radius of the moon, right? Half of its diameter. So the size of the moon has a relationship to its distance, right? To its distance. Well, notice this, because the light converges in the same place, right? Because they appear the same size, you can draw another triangle like this. I can extend this line all the way out to the sun. This is the distance to the sun. And I can draw it like this. I can draw it like this. So why is that so significant? Well, maybe you remember, we said in our early lessons, if you take two triangles, two right angle triangles, and you have them share an angle, right? So they share this angle here. That means that they share these angles too. This angle is the same too. It also means that the ratio of the sides is the same, right? If you were to divide the height by the base of the smaller triangle and the height and the base of the larger triangle, they would be the same. So what does that mean here? Well, the triangle that represents the sun's distance and sun radius shares an angle here with the triangle that represents the distance to the moon and the size of the moon. So you can see here that that means that the ratio, the proportion of the radius of the sun and its distance is the same to the radius of the moon to its distance. Let me write out that formula so it's a little easier for you to see. So the sun's radius is this line here, this purple line here, and the distance is this purple line. The moon's radius is this pink line here and this other faint pink line behind it. That's the moon distance. So we're saying that this radius, the sun radius divided by the distance to the sun, is the same ratio as the moon radius and the distance to the moon, right? Those are just sides of the triangle. And if you divide the two sides of a bigger or smaller triangle that share the same angle, if it's a right angle triangle, the ratios will be the same. Well, Aristarchus already showed us that the sun was 19 times further away. The sun distance was 19 times the moon distance. Well, in order for the ratios to stay the same, the radius also has to be 19 times. You have to multiply this entire side by 19 in order for this relationship to be true. So the nature of what we see in the sky, that they look to be the same size, and the fact that Aristarchus knows that they're 19 times further away, knows that he can demonstrate that with the size of the sun too. Now, we've already covered that. This is just a little bit of a different perspective, but let me show you next how he's able to use that to solve his next question, which is, what's the relationship between the shadow of the Earth and the Earth's diameter? So let's see how he's able to do that. Okay, so now let's apply some of those things we've learned to take our next step. So what I've drawn here is a lunar eclipse this time. In the last diagram, I showed you a solar eclipse. Now the Earth is getting between the sun and the moon. Now you remember this is what we covered in the last video. The moon was passing through the shadow of the Earth. That's what this white line is here. This white line is the shadow of the Earth at the distance to the moon, right? So we can think about this is the shadow of the Earth at the distance of the moon. And what we want to figure out is the relationship between this diameter or radius to the Earth's radius or diameter. So I've drawn the radius of the Earth, and so what we care about is the radius of the Earth's shadow in this case, at the distance to the moon. We know that there are 3 moon diameters that fit inside of the Earth's shadow. What is the relationship then between this Earth's shadow and the Earth itself? So that's what we want to find out now. Okay, let's add some components that will allow us to solve this problem. Let's start by drawing a line. I'm going to draw this line from the top of the Earth's shadow to the Earth itself. Now, you might be thinking, why did I draw this random line? Well, this isn't just a random line. This line represents the distance from the Earth to the moon. Remember, we're not just talking about the Earth's shadow anywhere in space. We're specifically interested in the Earth's shadow as it appears at a moon distance away from Earth. So this line here represents the distance from the Earth to the moon, right? This is the shadow as it appears a moon distance away. So that's number 1. Let's add another line here. We'll add a line from the top of the Earth to the sun. From the top of the Earth to the sun. Okay, this is the distance from the Earth to the sun. Remember, this is 19 times, according to Aristarchus, 19 times further away from the Earth, right? 19 times further away from the Earth. So this is the distance from the sun to the Earth. Okay, following me so far? I hope you are. Now, by the way, if you start at any point to see where this is going, feel free to pause and try and work it out for yourself. I really encourage that. Even if you're a little unsure, take pauses, try and work it out. It's really fun to try and see if you can figure these steps out. But don't feel bad if you don't see the next steps. These people we're looking at were geniuses, right? Part of their genius is their imagination and creativity and ability to take these geometric shapes that they know and think about how they apply in different situations. So they are geniuses for a reason. Now, hopefully you can follow along with some of these steps though. So let me start to add some more components. I'm going to now I want to label the radius of the sun too, just because that's going to be useful to us. So let me label the radius of the sun and just shrink this line a little bit. Now, what I hope you can start to see is something interesting. These 2 lines are parallel to one another. That means if you extended those lines in any direction, they would never touch. They would never touch. Now, what if we add a line that represents the light coming off of the sun that is just touching the Earth, that is causing the Earth's shadow, right? So remember, we looked at shadows and we looked at how the object blocking the light, right? How we can represent that by the light just touching the Earth. Well, you might now notice a bunch of really interesting things that are standing out. So definitely pause the video if you're seeing things and then come back when you're ready. Okay, so let me start to connect some dots for you. Remember, we said that these 2 lines are parallel, the green line and this orange line. The distance to the moon and the distance to the sun are parallel lines. And what you might be able to see is that we have a line now that intersects both of them, right? That goes through both of them. You could imagine extending this line, right? And now it passes through both. Well, we've already learned about this, right? We've learned about this rule. Let me just draw it for you. Remember, if you have 2 lines, 2 parallel lines, and you have another line that goes through them, do you remember something important about the angles? Do you remember that these angles here have to be the same? This angle has to be the same as this angle. these two angles are the same. I won't go through that proof again. We've done it in a previous video, but hopefully you remember this. Both of these angles have to be the same. In fact, this angle also has to be the same in this one too. Again, we've done the proof in a separate video. Well, what does that mean? That means that this angle here and this angle here are the same angle. And you might notice that we have two right angle triangles here. We have a right angle triangle here and a right angle triangle here. So we have two right angle triangles that share an angle in common. Well, we know what that means already. We know that that means that the ratio of these sides are the same, that there is a relationship between these two triangles. And in fact, we know that because this triangle includes the distance to the sun, and this one includes the distance to the moon, this triangle is 19 times larger than this one. The ratio of the sides is 19 times larger. So let's start to explain what some of these sides are, because this is really interesting. We want to know the relationship between this side here and this side here, and maybe can we figure out the relationship between this portion here and the radius of the Earth, right? This right angle triangle contains part of the radius of the Earth. Not all of it, but a portion of it. So what is this value and what is this value? Can we figure that out? Well, let's try. So I'm going to add one more line to our diagram. Let's add this first here. So this line is going to go from here, splitting all of these objects down the middle. Remember, in order for us to have this lunar eclipse, all of these objects have to be aligned perfectly, which means that we can connect their centers, right? Their centers are aligned. Now this line is parallel with all of our other distances, right? To the moon distance and to the sun distance. And so you might be able to start to see something interesting. You might be able to start to see that we can figure out how to relate these sides, because what we want to ultimately do is create a formula so that we can try and solve the problem of how do we relate the Earth radius to the Earth shadow and then the moon. Well, part of these triangles are the Earth radius, or part of the Earth's radius, and part of the sun's radius. But what are these parts? Because you can think about it this way. Purple, if you think about purple divided by green, purple divided by green is equal to, let's choose this color here, turquoise divided by orange. Let me write that equation so it's clear in our heads. Purple divided by green is equal to turquoise divided by orange. Can you see that? The purple line divided by the green line is equivalent to this turquoise line divided by the orange line, right? These two triangles share an angle, which means the ratio of the sides are the same. That's old news for us, right? We know that rule of trigonometry already. But in this case, these two portions. So the question is, what is the purple line? What is this purple line? Well, maybe you can see it here. Maybe you can see it. This is the radius of the Earth's shadow, right? This is the radius of the Earth's shadow here. This is the radius of the Earth's shadow. Well, you can see that that is also equivalent to this portion over here. So pink is equal to the Earth's shadow, the radius of the Earth's shadow. Well, what is purple? Purple is the radius of the Earth. It's what's left if you take the radius of the Earth and you subtract the radius of the Earth's shadow. Let me write that for us. Let me write that for us here. The purple line is if you take the Earth radius minus the Earth shadow radius. Do you see that? Purple is equal to the Earth radius minus the Earth shadow radius. It's what's left over. Well, you might see this next part too. Turquoise is equal to the sun radius minus the Earth radius. Do you see that? This is the Earth radius here. Well, if you take the sun radius, subtract this portion, which is the earth radius, you get the turquoise line. And green is our moon distance, and orange is our sun distance. So we can rewrite this formula. Let me just add all of our pieces here for us. So we know what purple is, we know what turquoise is. Let's add the other ones in here too. We know that green is equal to moon distance, and orange is equal to our sun distance. Orange is equal to sun distance. Orange is equal to sun distance. So we have all of the pieces for this formula. Let's just swap it in. If you want, take a second to pause, come back once you've done this yourself. So here we have it. I wonder if you got the same thing as me. This is just taking our formula up here, right? Purple divided by green is equal to turquoise divided by orange. Well, I've replaced purple with earth radius minus earth shadow radius over the moon distance, right? That's what the green one is. Well, that is equal to the sun radius minus the earth radius over the sun distance. I just substituted things in. And so now we're able to relate a ton of things together. We now have earth radius in our formula here. And there's lots of other stuff we know that we can start to substitute in. We know the relationship between the Earth's shadow's radius and the moon diameter, for example. We know the relationship between the moon's diameter and the moon distance. We also know the relationship between the moon and the sun. So I'm going to pause this week's episode here, and I want to see if you can start to substitute some things in. Can you simplify this formula more? Can you try replacing things and figure out relationships? Can you start to figure out these relationships so that you can start to narrow down an answer here, right? Our goal is to see, can we relate the radius of the Earth to the moon in some way? Through the Earth's shadow, but ultimately we want to get to the moon and then to the sun. So we'll pause here, and next time I'll show you how to finish this equation and this step. See you in the next episode.